Hi, I'm Reihan. In this video, I'll tell you about our SCCV 2023 paper, Controllable Visual-Tactile Synthesis. This is a joint work with Wenjin and Junyan. 3 simple steps to fill your sketch. First, draw a sketch. Second, choose a material, for example, the green skirt. Third, run our model. You will get a visual RGB image, a tactile geometry map, and auxiliary 3D meshes derived from the outputs. We train one model for each material. The zoom-in patch of the tactile surface normal shows the significant difference between distinguished textures. Here, we zoom in on the mesh to show more detailed 3D structures. We can render the generated visual and tactile output on a surface haptic device called canvas touch. The sound indicates the magnitude of the friction force. Here we show our data acquisition process. We obtain synchronized visual tactile data by registration with Aruko marker tracking. We use gel site R1.5 to capture tactile local geometry. The sensor outputs GS and GY represent the image gradient of surface normal in X and Y directions respectively. We use a Pi camera mounted on the top for visual capture and Aruko marker detection. The video shows a detailed demo. We used the gel site R1.5 sensor to collect tactile data. Its elastomer layer deforms with the object in contact, and behind the elastomer layer, an embedded camera captures the deformation as an RGB image. We then reconstruct the object's surface geometry using the photometric stereo principle. The screen on the left shows the real-time tactile reading. The upper RGB image shows the raw output captured by the sensor, and the lower grayscale image shows the reconstructed heat map. To spatially align visual and tactile data, we use a customized 2x2 grid of Aruko markers to track the sensor's location in the camera frame in real time. The screen on the right shows the visual data captured by the Pi camera. We detect individual poses of 4 Aruko markers, as shown by the 3-axis coordinate frames, and use RunSec to estimate the center point's 3D pose. Then we project the 3D center point to the 2D image frame and obtain the bounding box for the corresponding visual patch. During data collection for each object, we capture one visual image, randomly move the marker to different positions, and save the corresponding tactile data and bounding box coordinates. Here are examples of our collected data. For each object, we have one full sketch, one full visual image, and about 200 tactile patches covering about 1/6 of the total area. The bounding box of the patch is shown in the blue in the sketch. Given the coordinates from the marker tracking, we crop the sketch and the visual image accordingly to show the correspondence. Here's another material to show different textures. Our dataset contains 20 garments in total, covering various fabrics commonly seen in the market, such as denim, corduroy, linen, fleece, and knitted materials. We also cover diverse object colors and shapes, such as shirts, vests, sweaters, pants, shorts, and skirts. Given a sketch, we use the image-to-image translation method to generate synchronized visual and tactile output. We condition the visual image on sketch and condition the tactile output on visual and sketch. We use the full image to supervise the visual and cropped patches to supervise the tactile output. After getting the network output, we use a nonlinear mapping function and contrast enhancement to convert the 2-channel tactile output to a grayscale friction map that can be rendered on canvas touch device. We presented Controllable Visual-Tactile Synthesis, an image-to-image translation method to synthesize visual appearance and tactile geometry of different materials, given a handcrafted sketch. Visit our page for more cool visualizations, including interactive patch demo and text-guided generation with DALL-E 2.